All right, so isotopes. So think about this. All atoms of an element have the same number of protons. So that we know, don't we? Because that's kind of a defining characteristic, yeah, of that element. All atoms of that element have the same number of protons. But those atoms might have different numbers of neutrons. Isotopes, then, are two atoms of an element that have different numbers of protons. So it takes a little bit of time to sort of digest and sink in. Different atoms of a single element have the same number of protons, all of them. But those different atoms might have different numbers of neutrons. Okay? If you're an atom that has a different number of neutrons but the same number of protons, then you are isotopes of that element. Okay? Now, some isotopes of an element are radioactive. And that means that they spontaneously decay into something else. And when they spontaneously decay, usually they release something. They usually release a particle and some energy. And it just varies. Okay? Some isotopes are radioactive, some aren't. Some will emit one particle, some can emit something else. A common particle to be emitted by an isotope as it radioactively decays are things like electrons. They can be emitted. All right? And I'll tell you where those electrons come from. It gets kind of interesting. And there's always, anyway, some energy that's emitted, often in the form of gamma radiation. Everybody okay with an isotope then? We can look at some examples. So let's take a good look at good old carbon. All right? So far, the carbons that we've looked at, we've said, all right, carbon. It's got an atomic number of 12. Oh, an atomic mass of 12, sorry. An atomic number of 6. Okay? And when we look at the periodic table, we'll see, well, there's carbon. It's got the number 6. And it's got 12 point something. Yeah, and we're going to round to 12 for right now. So what does that tell us about carbon? How many protons does a carbon atom have? 6. Okay? Now, how many neutrons does this carbon atom have? 6. Everybody okay with that? Everybody okay with working out the number of protons if I give you the atomic mass and the atomic number? Yep. All right, good. But elements then, a chunk of carbon occurs as a mixture of its different isotopes. That means within a chunk of carbon, or any element, there are atoms that have exactly the same number of protons, but different atoms can have different numbers of neutrons. They're mixtures of different isotopes. Okay? So let's take carbon. Now, carbon can exist in several different forms, one of which is your diamond ring. The diamond in your ring is essentially one form of carbon. Another form is graphite. Now, think about this. Coal and soot are mostly carbon. Isn't it amazing you pay so much money for a diamond? It's basically just a lump of coal that's been exposed to excessively high temperatures and pressures, and it kind of turns it into diamond. How does that make you feel about your big old diamond ring? All right, so within a chunk of diamond, for example, in other words, within a chunk of carbon, there's a mixture of different carbon atoms, different isotopes of carbon. In the case of carbon, you've got about 89.89% of the atoms have 6 neutrons and are therefore carbon-12. About 1.11% of those carbon atoms have got 7 neutrons. Now we know carbon always has 6 protons, so what would be the atomic mass of an atom with 7 neutrons? 13. All right, guys, those of you who just walked in, we're doing the pass the rock around. If you've got a rock, it's your turn to answer a question. Once you've answered, pass it to your left. Okay? And a tiny fraction of those carbon atoms are, in fact, I'm not going to read out all those zeros, 0 point, lots of zeros, 1% of the carbon atoms in a chunk of diamond, for example, a chunk of carbon, have 8 neutrons. And that makes it carbon what? 14. Carbon 14. Okay? Now those proportions hold true for carbon, and they may certainly not be true for other elements. The elements are mixtures of their different isotopes. Okay? Yeah.
But the atomic number stays 6?
Yes. If this atomic number differs, it's no longer carbon, it's something else. Okay? All right. So, carbon 12 and carbon 13 are stable. In other words, there will be carbon 12 and carbon 13 for a long, long time. They're not going to change. But carbon 14 is radioactive, and it will decay and change into something else. How does that make you feel? Some of those carbon atoms in your diamond ring, over a period of time, are no longer going to be carbon. Your ring is getting smaller. What do you think about that? Make you happy? Maybe not. It's infinitesimally smaller. It's a tiny bit smaller. So let's now have a look at the periodic table, and we see that the atomic mass for carbon isn't exactly 12, is it? You can see those little numbers. It's 12.0107. Is that right? Is that what it is? Yeah? And we can take it to more decimal places for some. So, this explains why the atomic masses up there are typically not whole numbers. Atomic numbers are, because it's the number of protons. The atomic masses are not usually whole numbers. So if we've got about 98% this, about 1% this, and a tiny fraction this, we can kind of average these 3 numbers, taking into account the different amounts, and that gives us 12.0107 for carbon on average. Does that make sense? Now you know where these numbers come from. Yeah?
Is it possible for it to be like carbon 11? Or would that not be...
So I don't think there's a carbon 11. I don't think carbon 11 exists. It just doesn't exist. If it did, there would be a carbon 11, but it just doesn't exist. Okay?
Is it possible for like any of the elements to like have it go backwards? Because like, these ones are like it's 12 and then that, is there a way?
So yeah, I think some of the elements do have fewer numbers of neutrons than protons. Often we kind of start, especially with the smaller elements, smaller atoms, the same number of neutrons as protons. All right? Yeah. Okay. So, some isotopes then are unstable and they're radioactive and they decay into something else. Carbon 14 is our radioactive one. It decays, and it actually decays into nitrogen 14. Now, I don't want to get into too much depth about subatomic particles, and I don't certainly want to get into quarks and up quarks and down quarks and so on. So I'm going to keep it really simple, but as a result, it doesn't really tell you the whole or the full story. Okay, so just bear with me on that. Those of you who go take physics or chemistry classes, especially upper division ones, you'll go into this in an awful lot more depth that you perhaps need in those classes. So, what's the atomic number for nitrogen? 7. So somehow this carbon 14 changes into nitrogen 14. Somehow it gains a what? A proton. And what about a neutron? Does it have the same number of neutrons as carbon 14? It does? How many neutrons in carbon 14? It's got 6 protons.
It's got 8. Okay.
How many neutrons in carbon 14? 8. Let's have a look at nitrogen-14.
No, it has
How many protons does nitrogen-14 have?
7.
How many neutrons? All right. So here's what actually happens is one of these neutrons, you can think about it as a neutron as being kind of a proton and an electron sort of fused together. All right? So that neutron, which is made of a proton and an electron fused together, the electron is emitted, it's released, it goes. So one of these neutrons turns into a proton and an electron. The electron disappears, flies off. That's one of the radioactive particles which is released. Okay? And then the proton stays where it is. So that's why we get an additional proton. Is everybody okay with that? Yeah?
So it emits the electron and
Yep.
then the neutron.
You can think about it like this. Let's take one of these neutrons. And let's just say it equals a proton plus an electron.
Okay.
Okay? This neutron now changes into each of those. The proton stays in the nucleus. It's why it's got 7. And the electron disappears. If you've got that diamond ring on your finger, that electron is going to shoot right into your finger. Yeah, it does.
Now when that diamond starts to decay, is that what you get all the way it looks cloudy and everything else?
No. I honestly don't think, it doesn't make any difference at all to the structural integrity of the ring, as far as I know. All right? I don't think it makes it cloudy or... And there's radioactive particles shooting around all the time. All right? You don't feel them. And it also releases some gamma radiation. All right? It's normal background radiation. Now, I know I sort of focused on your diamond ring, but you have an awful lot of carbon in your bodies. Some of that carbon is carbon-12, some carbon-13, some carbon-14. And guess what? Those carbon-14 atoms are radioactively decaying in your body. And the electrons are shooting around in your organs, as is the gamma radiation. It's normal background radiation. Okay? Good? I just like to use a diamond example because all the girls are looking, oh, my ring's getting smaller. Okay, everybody okay with that? That process, how we can turn carbon-14 into nitrogen-14? Yep. Okay.
So does that happen with a lot?
Sorry?
Does that happen with a lot of the elements?
Many of the elements have radioactive isotopes, yes.
And they change into others?
Something else, yeah. Another element.
And that happens just as the elements, there's a bigger amount of them? Or like...
So every element, right, is composed of a mixture of isotopes. Some of the isotopes are common, some rare. Okay? And sometimes the isotopes are radioactive and are breaking down, but not always. Does that kind of answer your question?
Yeah, so does the process go faster as you have a bigger amount?
No. Here's the deal. The rate of radioactive decay, in other words, the rate at which this changes, never changes. Okay? There's nothing we can do to it to make it get faster or slower. You can heat it, you can put pressure on it, it decays at the same rate. It's kind of a remarkable thing because heat nearly always affects the rate of a chemical reaction, but this isn't a chemical reaction. Okay? It's interesting. I'll tell you what the half-life of carbon is. 5,730 years. So that tells you the rate of decay. Now let me explain this a bit further. We measure the rate of radioactive decay in what's known as half-lives. So the half-life is the amount of time that passes for half of the number of radioactive atoms to decay into something else. Does that make sense? So in your diamond ring, right now today, there's a certain amount of carbon-14, okay, presumably. Now, those carbon-14 atoms are radioactively decaying. They're changing into nitrogen-14. Half of the carbon-14 atoms will have decayed into nitrogen-14 in 5,730 years. Everyone okay with that? And then half of those will have changed and decayed in 5,730 years. Now that half-life, 5,730 years, is specific and unique for carbon-14 in carbon. Some elements, some isotopes, have a half-life measured in seconds or minutes. So the half-life of an element, the rate at which it decays, really varies. For some, it's seconds or minutes. For something like uranium, get this. Uranium, that's uranium-238, has got a half-life of 4.5 billion years. Very, very slow rate of radioactive decay. All right?
So half-life is a measurement of decay in radioactive elements.
Yeah, but be more specific than that. It's the amount of time it takes for half the number of the radioactive atoms to decay into something else. So let's just say in a chunk of your ring, I'll take an arbitrary number. You have 1 billion carbon-14 atoms. Let's just say you do. I guess that would be a pretty big ring, right? In 5,730 years, 500 million of those have decayed into nitrogen-14. Okay?
What would that look like?
What would your ring look like? I really don't know. I think that those little, nitrogen is a gas. You've got a nitrogen atom. I think it's just going to be locked up there in the middle of all the, other carbon atoms, not going anywhere. I don't think your ring will look cloudy. Maybe it might after 5,730 years. Yeah.
Is it like the smaller the atomic number, the shorter the half-life? Because
No.
you're going up in uranium. That's
Yeah, I
how-
don't know. There's no pattern to that. There isn't. As far as I know, there's no pattern.
Each have a different
I don't
half-life.
think there's a pattern. Sorry?
Each element has their own specific half-life in radio, and
Yes.
not the same at all.
No, there's no generic one. It's different. It depends on the element, depends on the isotope. And temperature or pressure doesn't speed it up or slow it down. Yeah.
So if there's something that's radioactive, like to us, like you have to stay away from it, would it be because the half-life is shorter than, or is relatively short?
No, so it has to do with, it has to do with the number of particles that are thrown out, the energy with which they're emitted, and the type of particle. So there's different types of radioactive decay, right? So some release particles that are very high energy and lots of them. Let's just say we've got a chunk of something and there are lots of radioactively decaying atoms, right? Lots of them. That means they're going to shoot out a lot of particles, right, with an awful lot of energy. So some of them have higher energy particles and more energy that they release on their radioactive decay, and there are more atoms decaying. Does that make sense? They're the ones that are more trouble for you. There's a background amount of radiation, but some elements are more radioactive because they've got more of the radioactive isotope in the sample, and they emit higher energy particles or radiation. Does that answer the question?
I think so, yeah. So that would be the one. So if it's something, so you're saying that something that is radioactive could contain a bunch of those, like carbon-14 atoms, and it just has a ton of them, so it's constantly emitting it?
Yeah. So things that we know sort of are dangerously, go to a nuclear reactor, for example, they use uranium. All right. Now that's a bit different what goes on in a nuclear reactor, but there are very high energy particles being released all over the place. All right. So, that's why the radiation is dangerous. It has to do with the number of particles, the amount of radiation that's released, and the energy of the particles in the radiation. Okay. Those two things combined make it, either dangerous or not so dangerous.
But isn't uranium like what they, so you said uranium is what they use to like power the plant? So
In a
would that
nuclear
mean
reactor.
uranium wouldn't that make it radioactive then? Or would that
So
just make the stuff?
most elements have a background level of radiation, right? But some are more radioactive. And with uranium, I can't honestly remember what happens in a nuclear reactor, but you're taking some of these very radioactive isotopes, right? So for example, you're going to take a very radioactive isotope of uranium, that one with 4.5 billion years. I don't think that's the one they're using. They're using a different isotope of uranium, but they're concentrating it. So the uranium they've got has an awful lot of the radioactive isotope, all right? And it's releasing particles all the time. And then what happens is when you concentrate it, because those particles are being released, they smash into the nuclei of other uranium atoms, and they bust the nucleus apart and change it into something else. And when that happens, it releases lots of heat energy, which is what, which is why we have a nuclear reactor, is simply to extract heat from it. Okay, that's a short answer to a long question. But, okay, good. Okay, all right. Now, different isotopes of an element chemically react in the same way. They don't behave different in a chemical reaction. All right. Any questions about isotopes then before we move on? Good. Okay. So now I want to talk about electron configuration, how the electrons are configured within an atom. All right, and the arrangements of electrons in atoms. And the reason why I want you to be okay with that is we're going to talk about chemical bonding afterwards. And how one atom chemically bonds to another one depends on its electron arrangement or the electron configuration. Okay, so let's have a look at electron configurations then. Electrons, remember, are negatively charged. They are tiny little particles with a very low mass, and they orbit the nucleus. They spin around the nucleus of the atom. Now, electrons have what's known as orbitals. And honestly, I'm not going to go into that in very much detail at all. I'm not going to go into these different orbitals that electrons have, but I want you to be familiar with this term orbital. Your book explains it if you want to know more about it, but for what we're doing in this class, I'm not that worried that you understand what orbitals are, except that electrons have orbitals, and each orbital is a certain distance from the nucleus and typically contains 2 electrons in an orbital. So there's a pair of electrons in each orbital, okay? Now, orbitals can combine together to form shells, electron shells. I'm going to be talking about electron shells primarily, and I want you to understand it in the context of electron shells. Now, when I talk about electron shells, that doesn't paint a super accurate picture of the atom. To get a picture of what it's really like, we've got to talk about orbitals, but that's probably another level of complexity I don't want to talk about in this class. So we're just going to talk about shells, but I want you to know that a shell is composed of orbitals. All right? All right, so we're only going to talk about shells from here on. I want you to understand shells. They're a lot simpler, easier to understand, and they're more conceptual than real. So when I talked about orbitals, so orbitals can have these shapes. Some of them are kind of these. I don't want you to think about that as like a planet orbiting the sun, but it's kind of like the skin of an orange. Yep. It's sort of spherical, and the nucleus is in the middle.
What time is it?
11:30.
Is this you?
Ooh, it's not me. Somebody left a watch in lab. Thank you.
Yep.
Is it expensive?
It was your lab. It's kind of nice.
All right.
Keep it.
I'm surprised you gave it back.
Salaries being as low as they are.
Exactly. Thank you. All right, so some of these orbitals are kind of this, like spherical, and some of them have this kind of shape. See that? Or this kind of shape. Okay? So don't worry too much about the orbitals. Orbitals combine and compose shells. All right, so let's talk about shells then. Electrons have shells. and we can talk about them in terms of a first shell. Some elements only have one shell, the first shell. Some elements have two shells. They've got a first shell and a second shell. And some elements have three shells, a first shell, a second shell, and a third shell. And we can go beyond three shells when we get to the bigger elements. Honestly, for most of the biologically important elements, we're talking about smaller atoms, and we're talking about what goes on in their first shell, second shell, and third shell. So I'm going to leave it at the first, second, and third shells. So, if here is the nucleus, and I'm not going to indicate how many protons or neutrons, because I'm going to use this as a generic nucleus for many different elements. Okay? Atoms can have shells. The first shell is the one that's closest to the nucleus, and it can only hold 2 electrons. It's full at 2 electrons. It can only hold 2. So give me an example of an element. You're going to need to look at the periodic table that only has 2 or fewer electrons. Give me an example of element that's got 2 or fewer electrons. Helium or hydrogen. Good. Helium and hydrogen. They've got atomic number 2. Hydrogen's got how many electrons? 1. Helium's got how many electrons? 2. So if I'm going to draw a hydrogen atom, I'm going to draw a single electron in that first shell. All right, this pen is no good anymore, is it? Where's the trash can? All right, watch this. Duck. One more go. Give it back.
The shell is the cloud that it's over in, the cloud.
Yeah.
Whatever. Oh, okay.
Yeah. It's not an easy shot that I might hit that line. Duck. Oh, not bad.
Well, you got it?
Yeah.
Oh, I wasn't sorry on that.
You're a non-believer, aren't you? You're a doubter. So here's hydrogen. This is the first shell, and there is 1 electron in that shell. Good? If you're helium, you've got 2 electrons. Well, both those electrons will go in that first shell. So, can this first shell have any more electrons?
No, sir.
Full. What happens if you're lithium? How many electrons does lithium have?
3.
It's got 3 electrons. Yeah, it's got an atomic number of 3 protons. It's neutral, so it's the same number of electrons. Where's that third electron going to go? In the second shell, the next shell, second shell. There we go. Now, how many electrons does this shell have? Can it hold, sorry?
8.
Max of 8, a max. So let's take good old carbon. How many electrons does carbon have? 6. All right. Is that 6 electrons? Total? All right. It's got 4 in its outermost shell, doesn't it? How many more electrons does it need to completely fill this outermost shell? How many more does it need?
4.
It needs 4 more, because it's full at... Good. Which element has 8 electrons in its second shell? Have a look at the periodic table.
Whatever E is. Whatever that is.
What is it?
Beryllium, I made that.
Ne? It's neon. It's neon. All right. Neon's got an atomic number of 10, which says it's got 10 electrons. Okay, which says it's got 10 electrons. So it's going to have 2 there, 8 there. What's going on with neon's outer shell?
It's totally full.
Totally full. Can it have any more electrons in it? No.
No vacancy.
All right. So here's the deal. When you have a full outer shell, you tend to be very stable. That's a stable place to be. So have a look at the periodic table. You see helium. it had 2 electrons in its outer shell, and that shell was full, yeah? Helium's very stable. In fact, so stable, it doesn't really interact. It doesn't really undergo any chemical reactions with anything else. Neon, its outer shell is full with 8 electrons. It doesn't react with anything else. Elements that don't react with other elements are called inert. All right? If you don't chemically react with anything else, you're inert. Okay, so if you know whether the outer shell is full of an element, you can make the call whether it's inert or not, can't you? Look at all of the elements in that last column of the periodic table. Helium, neon, argon, I think it's krypton, was it xenon and radon?
Yeah.
So all of those have a full outer shell, and they're all inert, non-reactive. All the other elements, they've got vacancies in their outer shell, and they are reactive. All right.
You call
Now,
them innards?
sorry?
Innards?
Inert.
Oh,
There you go, inert. How would you say that with an American accent?
inert.
Inert. You just kind of leave off the T, don't inert. There's some like sound at the end, which isn't really a letter sound, yeah? I don't know, maybe. I get poked fun of all the time. You don't mind me poking fun at you guys a little bit, do you? Okay, so atoms then that don't have a full outer shell tend to be reactive. How reactive they are varies. But when they undergo chemical reactions, those chemical reactions tend to fill the outer shell with electrons, and that makes them stable. All right. Is everybody okay with the filling rules for the shells? It's quite straightforward, isn't it? Yeah. So I want you to draw the shell diagram and all the electrons for lithium. Draw the shell diagram with all the electrons for lithium. There, I'll help you with this one. Just like that. Easy. So now I want you guys to draw carbon, neon, and oxygen. The shell configuration for those atoms. After drawing those three, you should get the hang of it. Yeah, I think so. All right, at least for elements with 3 shells and only 3 shells, you should be able to draw all of them. Yeah, for elements up to 3 shells. So 8 and 8 is 16, plus 2 is 18. So you should be able to draw any the shell diagrams for any of the elements up to argon, which has an atomic number of 18. Good? Okay. Does anybody want me to draw one, just to show you, to check it? Which one do you want me to show you? Oxygen. Okay. Oxygen, atomic number of 8. It's got 8 electrons. There's 1, 2.
That's the first shell, so it's only working off 2 shells right there, as you're showing.
We're going to use as many shells as we need, depends on the number of electrons, yeah? Let's always start by filling the first. First one fills at 2, second one fills at 6. Right? Sorry. Second one fills at 8, yeah. Yeah. I was jumping ahead.
What does the smaller circle represent?
The nucleus.
Okay.
Nucleus, there you go, where your protons and neutrons are. So let's do oxygen then. Well, there's 2 of the 8 electrons. So we've got, how many are going to go in the second shell? 6. 1, 2, 3, 4, 5, 6. There's oxygen.
So it doesn't matter like where, like how you put them in the circle. Like you can like kind of even them out.
All right. So
Constantly moving around regardless.
they're constantly moving. And in fact, electrons, they're very, in some ways you can think about them as being social. They like to hang out in pairs. You can draw it like that as well. Because this isn't really what it is. Conceptually, we're representing its shells. It doesn't matter where you draw them. The electrons are in orbitals, and they can jump around as well. All right? So we're just trying to sort of conceptually represent how they are. Is everyone okay with that? Oxygen. Good? With the electron configurations. Okay. So those outer shell electrons are called the valence electrons. And they're usually the ones that are involved in chemical bonding. So outer shell electrons are called the valence electrons, and that outer shell is called the valence shell.
So that's for covalent bonds.
Yep.
Then wouldn't it be BALE and CH?
Wouldn't it be what?
Wouldn't it, the second A, would that actually be an E?
Oh, it would. Sorry, it's a spelling mistake. Yes.
Do we need to know like the exceptions to the rules, like copper, when it
So-
comes to orbitals?
You mean when we start to get down to these bigger elements? So,
Will we
yes.
need to know that for biology?
not in 181. When you go take some more advanced biology classes or some more advanced chemistry classes, they're going to go into the electron configurations in other shells because, yeah, I know I've said 2, 8, 8. Well, you know what? It's not like that for all of the elements. Things change. It's always 2, it's always 8, but then it starts to get funky after that. Okay? For the elements that we deal with, from 1 to 18 atomic numbers, 2, 8, 8, done. Okay? For bigger elements, it's different. So here are the electron configurations then for all of those 1 through 18 elements. All right? And this diagram's in your book, but it's right up there as well.
So we don't have to drop this.
Sorry?
So we don't have to make a sketch of this in our notebook.
No, you don't need to make a sketch of this. Remember, all the PowerPoints are online. Yeah? Okay. Good. So there's your first. Now you can see how the periodic table's arranged. First shell in the row, second shell is the second row, third shell, third row. Yep, it is. I think so. All right. So now let's move on to concept 5, chemical bonds, chemical bonding. So you've got to understand the electron shells and electron shell configuration in order to understand the chemical bonding. All right, so chemical bonds. Chemical bonds hold atoms together. Atoms are held together with chemical bonds. And when one atom is chemically bonded to another atom, then we get a molecule. So think of a molecule as any entity where atoms are chemically bonded to each other. Okay, that's what forms a molecule. Now, a molecule can be quite simple. You can just have two atoms chemically bonded to each other. That will form a small molecule. Or you might have more than 50 atoms, or more than 1,000 atoms, all chemically bonded together. And that would obviously make a very big molecule. Okay? Everybody okay with the molecule then? It's pretty straightforward. Now, atoms form chemical bonds by either sharing or transferring electrons. They either share or transfer electrons. Now, there are other kinds of chemical bonds which don't transfer or don't share. But we're first going to talk about chemical bonds that involve sharing and transferring electrons in order to form the chemical bond. Anybody remember what this is?
That acid, or acid, whatever, right?
Formic acid.
Formic acid, good. And what's the atom right there?
Carbon.
Good. And what's missing right there? Chemical bond. Not really missing, we're just making it a more efficient way of drawing it. Okay? So, here we've got a molecule of formic acid. And each of these atoms is held, joined to another atom by a chemical bond. And each straight line is one chemical bond. In this case, it's one covalent bond. Okay? So, two together, we call that a double bond, double covalent bond. There's one bond, and there's the bond there not shown. Good? All right. So, now how many chemical bonds does oxygen always seem to form? Oxygen always forms two, doesn't it? Seem to. And carbon always seems to form how many? And hydrogen always seems to form how many? One. All right, so let's take carbon. Look at your electron configuration. How many electrons does carbon need to fill its valence shell? How many more does it need to fill its valence shell? 4. Carbon needs 4 electrons to fill its valence shell. Ooh, it makes 4 chemical bonds. What about oxygen? How many does oxygen need to fill its valence shell? It needs 2 more, doesn't it? Ooh, oxygen always forms 2 bonds. How many does hydrogen need to fill its valence shell? It needs 1 more electron, doesn't it? Yep. There's hydrogen. That first shell is full at 2. It needs 1. Well, hydrogen always forms 1 chemical bond. Everyone okay with that? So now you've got a rough way, at least, to see how many chemical bonds an element forms. Or put it the other way, if you know how many chemical bonds an element forms, you know how many electrons it needs to fill its outer shell. Okay? All right, there's a complex substance, isn't it? There's a complex molecule. So that's the structure of a substance called azithromycin, which is an antibiotic. Okay? And you can see there's a lot of carbons, a lot of hydrogens, a lot of oxygens, and
Nitrogen.
oh, we got a nitrogen. Can you see the nitrogen?
What was it, 2?
Couple. There's one there. One there. Any more? 2 nitrogens. How many chemical bonds, according to this, does nitrogen form? 3. How many electrons do you think it needs to fill its valence shell?
1.
It needs 3 more to fill its valence shell, right? Forms 3 bonds, needs 3 more. And again, if you look at nitrogen, atomic number is 7, it's got 7 electrons. 2 in the first shell, 5 in the second shell, so it needs 3 more to make 8, 3 bonds. Good? Okay. All right. So, lots and lots of atoms, lots and lots of elements, have incomplete valence shells. That means their valence shells have some vacancies. They're not full. So let's have a look at the periodic table. All of these ones over here, their outer shell is full. Okay? All the rest of them, and I'm just going to focus on these ones, all of these ones, their valence shells, they're as vacancies, they're not full. Okay? Those atoms can share or transfer valence electrons with other atoms to form chemical bonds. Now, whenever you share or transfer electrons, I wouldn't say the goal is, but I'm going to say that the goal or the end result is that both atoms have full outer shells. So when you share or transfer electrons in a chemical bond, the end result is that the atoms involved have full outer shells. Because having a full outer shell makes you stable. All right. So again, atoms form bonds by sharing or transferring electrons. And they share and transfer until they have full outer shells. So let's have a look at the different chemical bond types, and we'll have a look at how they form. Okay? So one bond type is called the covalent bond. Covalent bonds are very strong bonds, and biologically they're extremely important. You can almost think about covalent bonds as the bonds that literally hold you together. So we've got covalent bonds, which are very strong bonds. And then we've got ionic bonds, which are also very strong, except in water. You can think about water as being the kryptonite to ionic bonds. They're very weak in water. So both of those are strong bonds. And then we've got hydrogen bonds. Now, hydrogen bonds are weak bonds. And they're actually just weak forces of attraction. They don't involve the sharing or transferring of electrons. They're weak bonds and they're forces of attraction. Covalent bonds are the sharing bonds. Ionic bonds are the transferring electrons.
What do you mean by the forces of attraction? Like, they're just...
I'll go over each of these in more detail. I just want to give you a quick overview right now. And then we've got van der Waals forces, which are very weak bonds, and they're just very weak forces of attraction. So they're the four major chemical bond types that I'm going to talk about. I'm going to look at how they form and where they're relevant and important. Okay. All right, so first let's look at covalent bonds. So a covalent bond then is where a pair of electrons is shared by two atoms. It's where a pair of electrons is shared by two atoms. And when they share those pair of electrons, that will either fill or contribute towards filling their valence shells. Okay? So usually atoms will continue to share electrons to fill their valence shells. And we'll look at mechanically how that works. Okay? All right, so I'll play this video first. I think this shows it really nice. It's an animation. Let me get the audio up a little bit.
A covalent bond is the sharing of a pair of outer shell electrons by two atoms. For example, each of it needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bonds. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound, a substance formed by the combination of 2 or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs 2 additional electrons to fill its outer shell. Thus it can form 2 single covalent bonds. An oxygen atom can share electrons with 2 hydrogen atoms, forming a molecule of water containing 2 single covalent bonds.
Does that help? Sort of visualize how they share pairs of electrons to fill their outer shells. So have a look at this now. See the outer shell of oxygen? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oop, I miscounted 9. 2, 4, 6, 8. There's only 8 electrons there in that outer shell. Yep. 6 of them were from oxygen, 2 of them from hydrogen, 1 from this hydrogen atom and 1 from this hydrogen atom. Now you can see why water is H2O. Yep, 1 oxygen with 2 hydrogens. Is everyone okay with that? So any questions then about covalent bonds? I think it's quite straightforward, isn't it? Yep. Sure? Okay. All right. So here's a molecule of hydrogen. You can see the outer shell electrons. That pair is shared, which means 1 covalent bond between the 2 hydrogens. And that's why we draw it with 1 stick like that. We can also draw it like this. There's the shared pair of electrons. Those 2 dots each represent an electron. Okay? Good? That's what oxygen would look like, represented in the same way. Oxygen, double bond. There's our 2 paired shared pairs. And then we got 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Okay. Good. Water, and of course, last but by no means least, one of my favourites. What's this substance? What's that? Methane. That's the right way to say it. What's methane? All right, methane. Okay. Good. So, do you reckon formic acid, you could draw the electron configurations? It's not that much more complicated, is it? Yeah. If you want some practice, go back and look at the formic acid molecule and draw the outer shell electrons for each of the atoms if you want some practice as homework. All right. So every atom then has got a characteristic number of covalent bonds that it can form. And we call that the atom's valence. And we've already talked about the valency of different atoms, haven't we? How many chemical bonds does hydrogen form? 1. So it's got a valency of 1. And then oxygen can form how many? 2. It's got a valency of 2. Nitrogen can form how many?
3.
3. It's got a valency of 3. Carbon can form 4. It's got a valency of 4. Okay, hydrogen 1, oxygen 2, nitrogen 3, carbon 4. So now this molecule makes sense, doesn't it? You can see for every one of those atoms, it forms this typical number of bonds. Okay? And this is actually an amino acid called alanine. It's the chemical structure of an amino acid called alanine, which makes up, is a part of protein. Many proteins contain the amino acid alanine. It's the most simple, one of the most simple amino acids. All right. Is everybody okay with this part where we just got CH3? How would that look if we drew it out in full stick diagram?
Just look like
You see
little dashes.
Like that, yep. Okay. Yep.
Okay, I'm just confused on the nitrogen. Why is that 3? Because the number is 7.
So let's do nitrogen then. What's the atomic number of nitrogen? 7.
So there's 2 on the first.
How many electrons does nitrogen have then? 7. So the first shell fills at 2.
2 right there.
So how many more have we got?
Okay, I get 3.
Good. 1, 2, 3, 4, 5. In the second shell,
Then it's not having
it needs 3 more to fill it. Good. Okay. Now, atoms in a molecule attract electrons to varying degrees. When electrons are shared, it's because there's an attraction of atoms for those electrons in the other atoms. The degree of attraction between atoms varies. And so we've got this term electronegativity. Now think about electronegativity. That's the attraction of one atom for the electrons in another atom. That's what electronegativity is. So atoms attract the electrons of other atoms, some of them. And some of them strongly attract the electrons in other atoms, and some of them not so strongly. The attraction of the electrons for another atom is called electronegativity. Some atoms are highly electronegative, some weakly electronegative. Okay? Now, the more electronegative an atom is, in other words, the more strongly it pulls those electrons towards it, the closer those electrons will be to the nucleus of that atom. Right, is everybody okay with the concept of electronegativity? So let's think about this then. I'm going to take water, for example.
Someone says that an electronegative an atom more strongly it pulls and compacts. Does that mean the shells just get smaller and tighter around the nucleus? And I'm not.
Let's say, yeah, they do. It doesn't work like that, but you can conceptually, you can imagine it like that, yes. It doesn't quite work like that, though. But conceptually, you can. So here's the one covalent bond. There's the shared pair of electrons. Here we've got 2 different atoms. The bond is between 2 different atoms. These have different electronegativities. One pulls the electrons more strongly than the other one. In this case, oxygen is very highly electronegative. It pulls the electrons towards it more than hydrogen. Imagine it like this. Here's the 6-year-old brother. Here's the 2-year-old brother. They got a teddy bear. And they got a tug of war. Teddy bear's going to end up over here, isn't it? Yep. Think about that with electronegativities. So the electrons are going to stay more concentrated around the oxygen and much less so around the hydrogen. That's the shared ones. Okay? All right. So you're okay with that concept of electronegativity? So we're able to measure the electronegativity for atoms and give it a value. And the scale is from 1 to 4. I don't know why it's from 1 to 4. It's kind of funny. Insect stings are rated on a scale of 1 to 4. Don't know why. We have an insect in Arizona called a Pepsis wasp. It's a big, sort of brownish, reddish colour wasp about this big. They're called tarantula hawks, and their sting is number 4. It's on the most painful scale. There are bullet ants that we encounter in the jungles in Costa Rica. Their sting, number 4. Okay, fluorine then. Top of the scale. The most electronegative atom out there. It's got an electronegativity of number 4. 4. It's the most highly electronegative atom we've got. Okay. And then oxygen is also pretty electronegative. On that scale, it's 3.5. And then we've got nitrogen shortly behind oxygen at 3. What is S? Sulfur and C for are both at 2.5, kind of roughly in the middle. Weakly electronegative. Now let's go right down. What's P? Phosphorus and H. Hydrogen, quite low on the electronegativity scale of 2.1. And then you've got lithium, rock bottom at 1. Lithium being rock bottom, and then many of the other elements form somewhere in between these ones. These are just representative ones. Yeah, they're important biologically. Poor old lithium has such a low attraction for the electrons that it can barely hold on to its own outer electron. Barely holds on to it weakly. Fluorine, on the other hand, so highly electronegative, let me tell you, if there's an electron anywhere close to it, pulls it in. Okay? So that gives you an idea of what electronegativity is, yeah? All right, so that's important. So now we're going to apply electronegativities to covalent bonds. Okay? Do you need a little break? Got a question?
No, it's just a lot.
Tiz. Is it a lot? Tiz, what you'll find is a lot of content coming quite quickly, but it's all quite logical, thankfully. Question?
An easy way to tell is just by looking at the noble gases, the further away to the left on the table of elements, or the periodic table, is the further away from the noble gases it is, the weaker it is. It's just
Got it. Yep.
an easier way if you forget to look
Yep.
at it.
So I like that tip. Over here, these ones are all quite highly electronegative. And as we go in this direction, they get progressively less electronegative. And over here are the least electronegative for their rows. Yep. Okay. All right. Good. You got any questions? Now's a good time to say, all right, it's a lot of information. Let's process it a little bit. Ask any questions. No? Yeah? I know what those little smiles mean. They usually means, I've got lots of questions. Now's the time to ask. Don't be shy. Good? Okay. So, non-polar covalent bonds. If the electrons in the covalent bond are equally shared, you've got two 6-year-olds, identical twins, tug of war over the teddy bear. Teddy bear is going to be right in the middle, equally shared. Then we call that a non-polar covalent bond. Let's take a covalent bond between two hydrogens. What's the electronegativity of hydrogen? Anyone remember?
2.1.
2.1, 2.1. Well, their electronegativities are identical. They both have an equal pull on these shared electrons, right? So I'm going to change this to the electrons. Because this atom has an equal attraction for these two that this one does, they're shared right in the middle. Is everyone okay with that? And as a result, that's called a non-polar covalent bond. So if this is the covalent bond, this line, there is no polarity across that bond. One end of it is no more negative or positive than the other end of it. That's what I want you to think about it like. Okay? Let's take oxygen. What's the electronegativity of oxygen? 3.5, 3.5. Well, same electronegativities. These are exactly equally shared. Electrons right in the middle, a non-polar covalent bond. Yep.
Is that like in those other pictures where there's the lines at the bonds?
Oh, where it went like this, you mean?
Yeah, like that. Does that mean it's like this?
No.
Shell
That's actually a covalent bond. But it's designed to represent that it's sort of three-dimensional. It's going off into the page or down into the page. Yeah.
Well, we need to memorize these numbers, the electronegativity of these.
So I wouldn't expect you to memorize these electronegativity values. I wouldn't. But what I do want you to remember is which are the very highly electronegative elements and which are the less so. It's actually very easy. The ones that are biologically important, I'm jumping the gun a little bit, but I'll tell you since you asked the question. The biologically important atoms that are highly electronegative are oxygen and nitrogen. That's easy to remember, isn't it? Most of the other ones, fairly low on the electronegativity scale. Okay? All right. So, covalent bonds then between atoms of the same element are always going to be non-polar covalent bonds, right? Because they've got the same electronegativities. What happens though if the electronegativities between the two atoms is very, very similar? For example, carbon always seems to bond, or often seems to bond, with hydrogen, doesn't it? What's the electronegativity of carbon? 2.5. What's the electronegativity of hydrogen? 2.1. These aren't identical, are they? But they are very, very similar. So, when the covalent bond is between atoms of the same element, the same electronegativities, it's a non-polar bond, yeah? When the covalent bond is between atoms of very, very similar electronegativities, it's also a non-covalent, non-polar covalent bond. Now, don't ask me what the cutoff point is, because it's kind of a sliding scale. What do you think the sort of opposite is to non-polar covalent bond? A polar covalent bond. We haven't talked about those yet, but it's sort of a matter of degrees. So the electrons, they're not going to be right in the middle, are they? But where are they going to be? Skewed slightly. Slightly over here.
But almost like unnoticeable. Is that what
Only a tiny amount. So we call this a non-polar covalent bond, even though they are ever so slightly close to the carbon. And in fact, it does create a slightly, ever so slightly more negative side there than over here, because the electrons being negatively charged are more closely clumped over here than over there. So, if the covalent bond is between atoms of very similar electronegativities, like carbon and hydrogen, then we would expect a non-polar covalent bond. Wunderbar? Good. Okay, let's wrap it up there.